Welcome to lecture 17. We are studying electronic devices and circuits, and today we will derive expressions for voltage and current gain of a voltage divider bias configuration without emitter bypass capacitor. This is the schematic of the circuit where we do not have a bypass capacitor for RE. This means that both DC and AC currents they pass through RE. So we have to take the effect of RE while we compute voltage and current gain. This is the equivalent linear circuit for this configuration. We have already studied this circuit in our last lecture, lecture 16. R1 and R2 appear to be in parallel with each other because this capacitor acts like a short circuit for AC, and when we apply this AC analysis, we apply superposition theorem and this VCC is replaced with a ground. So we have these R1 and R2 in parallel with each other. Here we have this small Re, the junction resistance, small Re. When seen on the side of the input side, it's multiplied with beta. So it becomes beta Re. So between base and emitter terminal, this is base and this is emitter terminal. Between these two terminals, we have only Re. When seen on the base side, is multiplied with a beta. And from emitter to ground, this is ground. We have a resistor Re. When seen on the base side, is multiplied with beta. When seen on the output side, isn't multiplied with beta. So therefore, I have put beta in a dotted circle. On the output side is collector. Since it's a common emitter configuration, the output is a collector. The output is taken from the collector. From collector to ground, we have this resistor RC in parallel with RL plus in parallel with the resistor R0, that is the resistance of this terminal with respect to ground. So this is the circuit we have, which we have already studied. This is collector terminal. So let's compute the voltage gain for this configuration. In our earlier lectures, we have studied that the stage voltage gain AVS is the ratio between VL, the AC output voltage, VL, the voltage drop across load resistor, divided by the voltage of the supply voltage VS, right? VL over VS. So if we compute VL and divide by VS, we get an expression. So let's compute this expression. VL is the voltage drop across the load resistor. Since load resistor RC and R0 are in parallel, so VL is also the voltage drop across the parallel combination of these three resistors. The current that flows through this parallel combination is beta IB. It comes down from here. The input current becomes IB, beta IB plus IB, almost beta IB, because beta IB is very large compared to IB. So since the current is beta plus 1 times IB here, but we take it beta IB for simplicity, this beta IB current takes this path and enters into this parallel combination. So the voltage drop VL would be beta plus 1 IB or beta IB times R0 in parallel with RC in parallel with RL. Since R0 is very large compared to this parallel combination, we usually neglect it and we are left with this expression for VL. Now, if we put IB in terms of VS, we can compute stage voltage gain directly. What is IB? Is the current that flows through the base terminal. The resistance small Re and this capital Re seen on the base side, they are multiplied with beta. So since they all are in parallel, Vs is the same node Vs, and even here we have the same voltage Vs. So finding IB, that is the current flowing through it, would be simply by applying Ohm's law. IB would be is Vs divided by the resistance of the path. Beta Re plus beta Re, beta times small re plus capital Re. So if we put this value of Ip here, we can straight away compute VL over Vs. VL becomes beta times Ip, which is Vs over beta times Re plus Re times Rc in parallel with Rl. This beta cancels with this beta, and if we take Vs on the other side, it becomes VL over Vs, which we also call AV stage, is Rc in parallel with Rl over Re plus this capital R. So this is an expression for stage voltage gain for this configuration with where Re is not bypassed by a capacitor. The other thing that we will do in this lecture is we'll find out stage current gain AIS like AVS, which is the ratio between the output voltage and the input voltage. Stage current gain would be AIS is the ratio between IL over IS. IL is the current that flows through minus sign because voltage gain is negative because the direction of current is produces a voltage that is opposite to the desired voltage. If we want to put a negative sign here. So AIS, IL over IS would be IL is the current flowing through resistor RL. How do you find this current when we have this beta IP current? Beta IP current entering into this parallel combination. Since the value of R0 is very large, we neglect it. So this beta IP enters into this parallel combination. So according to current divider's rule, IL would be RC over RC plus RL times the total current beta IP. And we have to find it in terms of IS. How would you write IP in terms of IS? IS is the total current that enters into this junction. Part of it flows through R1, part of it flows through R2, and the remaining current flows through this series combination. So, according to current divider's rule, we can write IP in terms of IS. These two resistors can be combined together and can be written as R1 in parallel with R2. So now we have this IS current that divides between this parallel combination and this combination. So it has two paths. We can replace it with one resistor that is R1 in parallel with R2 and get rid of this other resistor. So R1 in parallel with R2. So now we have two paths. This IS divides. Part of it flows through this path, part of it flows through this path. So since we are interested in this current, we'll write the other resistor in numerator according to current divider's rule. R1 parallel with R2, R1 parallel with R2 plus the distance of this path, beta times Re plus Re times the total current Is. This is IB written in terms of IS. Now we are almost done because now we'll put the value of IB here. Plugging the value of IB here will give us IL in terms of IS. So that puts this value here, IB. Let's replace this IB with this whole stuff. R1 in parallel with R2 or R1 in parallel with R2 plus beta times RE plus RE times IS. Right. So now if we divide IS here, this becomes IL over IS, and this is beta times this current divider expression times this current divider term, this term and this term. Both these terms are less than 1. This gives us a value that is slightly lesser than beta, but since it offers a good current gain. So in our earlier lectures, we have studied that the common emitter configuration and the common emitter configuration offers both voltage and current gains. In the next lecture, we will study voltage expressions for voltage and current gain for voltage divider biased configuration where we have an emitter bypass capacitor. Thank you.